All right, looking at repeated games. So repeated games are when we have a simultaneous game like a prisoner's dilemma that is played repeatedly. And what that means is that now the strategies that the players adopt are potentially going to change. All right. In this sense, the strategies are temporal. There might be a new strategy that the players adopt for the entirety of the game, or it could be that the strategies that they adopt change as the game goes on, depending on what round it's in. All right. So in these types of repeated games, we have ones that are finitely repeated, so they don't last forever, and the players know the number of rounds over which the game will be played. And then we also have infinitely repeated games. This is when a simultaneous game is going to last forever, so the rounds aren't known. So our class is going to be a finitely repeated game where we're only meeting for the semester. However, your relationship with me is potentially an infinitely repeated game, or at least we're not sure when it's going to end, right? Even if the class ends the semester, perhaps, you want to take another class with me, or we're going to be interacting around campus, or whatever that might be. And so your behavior is going to adjust based on those expectations, right? That's why sometimes we see folks who are graduating get what is called senioritis sometimes, at least it was when I was in school, where the seniors start to behave not as nicely, right? Whether they're less deferential to the faculty or they are less bought into the class itself, because they're anticipating the end of the game, right? They're anticipating graduating and leaving and not necessarily coming back to interact with the folks at that university. I will say if you have any plans to live in the same area as the school you go to, or um, maybe go into grad school, graduation does not represent the end of your relationship often with faculty, right? Okay, so let's focus first on finitely repeated games. So again, these are when the players know the number of rounds that the game will be played, and it's more than one round. All right. So and in this case, the strategies are going to vary depending on the period. In these games, we often see players use what's called backwards induction. So it's a process of solving a multi-step game by first solving the last step and then working backwards, excuse me. So the players are going to anticipate what move they want to make in the final round. Likewise, they're anticipating what move their opponent is going to want to take in the final round, and they're going to backwards induce from there what they want to do the round before that, the round before that, the round before that. Okay. What we often see as a result of backwards induction is that cooperation unravels because players know when the game is going to end. All right. And so they're likely going to defect to sort of gain a last advantage in that last round. But both of them are going to know that and anticipate it, so they're going to try to defect in the second to last round, which again, they both know that they have an incentive to do. And so that defection goes back, 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 back until cooperation never starts in the first place. All right. So we see this very clearly in what's called the centipede game. This, rather than being a simultaneous game, is a sequential game, but it can show us how backwards induction causes the game to unravel. All right. So again, if the centipede is a sequential game, that means that one player moves and then the next, right? They're not moving at the same time. So what we see is that as players move sequentially in this centipede game, they're choosing whether to pass on a pot of money to the next player or keep it for themselves, right? So we call that choice to pass is the action pass, and the choice to keep it for themselves is the choice to pull. So if a player pulls, the pot is going to be less for the next player than if they'd passed. And so the standard form of this game is for it to be played 100 rounds. And the best equilibrium, like the optimal equilibrium for each player, is that if they cooperate for all 100 rounds, then they earn a payoff often of $100, right? Um, what we're going to see, however, is that the players are both going to know that the game ends after 100 rounds, and both have an incentive to pull before that last round. And so we see the game unravel such that there is no cooperation. Okay, so here on the slide, you can see a visual of this game. Player one starts. They can either choose to pass or pull. If they pass, player two has that same choice to pass or pull. If they pull, player one gets nothing and player two gets $3, right? If they pass on the pot and it builds and builds and builds, as you can see, until that 100th round, where if player two passes, both get $100. But if on that last round, player two pulls, they can increase their payoff by one, right? They get 101 now, but player one only gets 98. So knowing that player one's going to pull their their move before player two's last move, so that they get 99, and player two also gets 99. And then player two, knowing that, is going to pull before player one's last move, so they get 100 and player one gets 97. And again, player one, knowing that, is going to pull before that choice for player two to ensure that they get 98, and so on and so on and so on, until at the very onset of the game, player one doesn't even pass, they just pull, and they both get $1. Right. I should say that is the game theoretic prediction for this game, using players who are strictly self-interested and again have symmetric knowledge or information about the game. When this game happens in experiments in the lab, that is not often what happens. What happens is that there is some degree of cooperation that players are able to sustain for a good chunk of the game. And sometimes experiments have even found that players cooperate all 100 rounds. All right. So one thing we can talk about as we get into the later videos, especially with our last one, that's going to be focused on how can players increase cooperation. We're going to talk about why, when we test these games in the lab, we're not necessarily going to see the outcomes that game theory predicts. All right. So just keep that in mind that that's coming. But again, the strict game theoretic prediction for this centipede game is that player one first move just pulls the pot for themselves and the game is over, and both players get $1. All right. So when we have infinitely repeated games now, neither player knows when the game is going to end. They don't know the number of rounds that it's going to play. This means that they are more likely to sustain cooperation because they don't know when that last round is going to be, so they can't anticipate when they can defect without facing too much of a consequence. So the degree of cooperation that we see is going to ultimately depend on how a player values the future. We call this their discount rate, right? How do they discount future payoffs? All right. If we look at the advertising game from previously, we found that the Nash equilibrium was advertise. When the Warner Brothers and Disney play this game just a single time, and they each get 250 million. Right. What we're going to do now is see that if these two companies play this game repeatedly on an infinite time horizon, right? They don't know when it's going to end. Can they sustain cooperation such that they both don't advertise and earn 70 million more, right? Such that they earn 320 million each. Okay. So let's walk through what would be required here. So one of the important assumptions we're going to make is that the payoffs are constant over time, right? These aren't going to change as the rounds progress. Every single round, we're going to have the same payoffs. And so what is going to determine whether the two firms cooperate, and again, if they don't advertise, will be if their payoffs from cooperating over time are greater than their payoffs from defecting. Okay. Like I mentioned previously, whether those gains from cooperating are worth it is going to depend on the discount rate that the firms apply to future earnings, right? So what we're going to do is try to find that discount rate, right? To see what it would need to be for cooperation to be sustained. And this discount rate is going to be between 0 and 1 meaning that a dollar today is worth more than a dollar tomorrow, right? A dollar tomorrow is worth, some fraction of a dollar today. So the present returns are valued more than future returns, right? That's why we often see cooperation collapse because people are valuing, short-term gain over long-term gain, right? Okay. So as the value of D, that discount rate increases, it means that people are valuing the future more and more and more. So the closer it gets to 1, the more likely that people cooperate. The closer it is to 0, the less our players care about the future and the less likely they cooperate in the long run. Okay. So when we're seeing what that discount rate would need to be, we want to identify one, what the firm's payoff from defecting is, right? That's what usually happens in the single shot game, right? It's paid one time, it's not repeated. We see both firms defect and they advertise and thus reduce their overall gains by 70 million. We want to compare that to their payoff from cooperating over time. So we're going to have that initial payoff, if we focus on first the payoff from defecting, that initial 550 that one of the firms would get when their opponent doesn't advertise, but they do. And then from there, they're going to earn that payoff from defecting, the advertising payoff, because the idea is that after they defect, their opponent is also going to start advertising and cooperation can't be regained. All right. For cooperating, we're going to assume that they're staying perpetually in the don't advertise, sell. They get 320 to begin with, and then we want to see how that is discounted in the future. And one thing you'll see here is that with each round, our discount rate grows. So the first round, there's no discount rate. Second round, there is. Third round, that discount rate is squared. Fourth round, it's cubed, right? So what you can see is that as the rounds get further and further in the future, they're discounted more heavily, right? That's again just showing that present earnings are valued more than future earnings. So for cooperation to be sustained, we need the payoff from cooperating to be greater than the payoff from defection. All right, so that's what is shown here in this second bullet. That payoff from cooperating here is greater than the payoff from defecting. So to know what that discount rate needs to be for cooperation to be sustained, we just solve for D. All right. So here we're just going to solve for our unknown in this inequality. So we're going to start by subtracting 320 from both sides. And we're also going to subtract the payoffs from defecting. Okay. That way we're left with a constant on the right-hand side and our variable on the left. And what we've done in this second equation here is we've subtracted the difference between 320 and 250, which are both modifying d squared, d cubed, and so on. And we've pulled that out of the parenthetical, right? So that $70 difference is applied to each of our discount rates here. All right. Next, we're going to move that constant 70 to our right-hand side by dividing both sides by 70. That's going to get us just the sum of our discount rates, which need to be greater than 23/7. This is where you need to remember that from your math classes that we can represent an infinite series when the variables between 0 and 1 by this expression here, right? We can represent that infinite series as d over 1 minus d. Okay, so we're going to substitute that on our left-hand side. That's going to get us d over 1 minus d greater than 23/7. Again, we're solving for d, so we want to get rid of that fraction. So we're going to multiply both sides by 1 minus d. That gives us d greater than 23/7 times 1 minus d. And then we're just going to distribute. So we'll distribute that 23/7 into that parenthetical, right? So previously we had this here, d greater than 1 minus D times 23 over 7, and we just distributed that 23 over 7. Okay, so we get 23 over 7 minus 23 over 7 times D. We're going to add 23 over 7 times D to both sides. That's going to get us 1 times D, which we can represent as 7 over 7, plus 23 over 7 times D. Solving, excuse me, and that is going to be greater than 23 over 7. So combining like terms on our left-hand side gives us 30 over 7 times D, which is greater than 23 over 7. We want to isolate D, so we're going to multiply both sides by 7 over 30. That's going to give us that D is greater than 23 over 7 times 7 over 30. Those 7s are going to cancel out such that we get that D needs to be greater than 23 over 7, which is equal to 0.77. So as long as, what this means is that as long as Disney and Warner Brothers view a dollar earned in the next period to be worth as much as 70 cents today, they're going to sustain cooperation. So that's a fairly high discount rate, right? They need to value a dollar tomorrow at 77 cents at least. Okay. All right. So with that, we're going to stop our video on repeated games. And then in the next video, we'll look at the strategies, different strategies that players can adopt.